In this paper, we study and develop active learning methods for online training of machine learning models with credit card fraud detection in mind, where often there is a very large class imbalance. We also consider a streaming scenario that we are under cold start, which means that there is no labeled data to start with, but there is lots of unlabeled data streaming into the system. Active learning in this scenario addresses the following question. What is the smallest sample that we can label to train a high-performance model in a system deployed for the first time? More specifically, in this scenario is useful when there is a delay between the event and the label collection. For example, in fraud detection, client complaints that provide that label can take from days to weeks or even months to arrive. It is also useful if producing labels faster than just waiting for these client complaints is costly. For example, by sending events to human analysts for faster labeling. So it is important to choose wisely what to label first. Finally, active learning is useful when there is plenty of unlabeled data available to choose from. So again, it is important to prioritize what to label first. These conditions often hold for new clients in credit card fraud detection. Our main contribution in this paper is an active learning annotation strategy for datasets with orders of magnitude of class imbalance in a cold start streaming scenario. More specifically, we develop an outlier-based discriminative active learning approach, ODAL, to be used as warm-up in a 3-stage sequence of AL policies. And 2, we perform an empirical study of policy sequences for real-world credit card fraud datasets. Our ODAL warm-up method is a modification of the discriminative active learning method that first trains the discriminative model between the labeled and the unlabeled data, and then prioritizes for labeling the unlabeled data that is easiest to discriminate from the labeled data. That method has a shortcoming that it scales with the unlabeled data size at train time. So instead, we propose ODAL, where we train an outlier detection algorithm on the small labeled data pool, and then select the most outlying instances in the unlabeled data. In our experiments, we rank several sequences of up to 3 AL policies, where ODAL is included as warm-up. We rank the sequences for several datasets representing different fraud detection subdomains and use the average ranking to sort the sequences. We also include an optimistic policy, that is baseline policy, that assumes access to all labels for all the dataset. Our main conclusions are that our sequences can more quickly achieve a high-performance model compared with sequences without ODAL. The gains over random sampling can reach up to 80% in this domain, and the performance similar to the optimistic baseline is obtained with just a few % of the labels. Thank you, and see the paper for further details.